faithfully conveying value and interpreting great books from around the world.
Hello, this is Sally's Book Talk.
Today, we're exploring the book Space Settlers, subtitled How Will Humanity Settle in the Infinite Universe? In 2021, we witnessed an extraordinarily remarkable year in human spaceflight history. China successfully launched the Tianhe core module of its space station into near-Earth orbit, and the James Webb Space Telescope, Hubble's successor, was successfully deployed. The Hope, Zhurong, and Perseverance probes successfully visited Mars against the backdrop of increasingly frequent human space activities. Becoming space settlers traveling through the cosmos may soon transition from fantasy to reality. This book explores how humanity will overcome immense challenges to pioneer new living spaces in space. The author is renowned American science writer and journalist Christopher Wanjek. He served as senior writer at NASA's Goddard Space Flight Center, extensively covering cosmic structure and evolution. Upon publication, this book received widespread acclaim and was named a 2020 Book of the Year by the Daily Telegraph. The author systematically analyzes barriers to space access, challenges of space settlement, explores future space travel models, and enhances our understanding of space habitation. Now, I'll interpret this book through 4 sections. First, why should humanity go to space? Second, what challenges does space travel face? Third, how do we reach space? Fourth, how do we establish settlements in space? Let's begin with part 1. Why should we venture into space? Konstantin Tsiolkovsky, founder of modern astronautics and father of Soviet spaceflight, famously said, "Earth is humanity's cradle, but one cannot remain in the cradle forever." Earth's unique combination of air, water, sunlight, humidity, atmospheric pressure, gravity, and cosmic radiation is unparalleled. After billions of years of evolution, life has perfectly adapted to Earth's environment. Leaving this planet poses extreme threats to human survival.
So why would humanity take such risks to go to space?
Space advocates contend Earth faces critical overpopulation and resource scarcity issues. In the early 21st century, global population surpassed 7 billion, with projections nearing 12 billion by 2010. Conflicts sparked by resource competition are constantly unfolding on Earth. If humanity can explore and develop space to expand living space and resources, such problems would be easily resolved. Secondly, Earth is not an absolutely safe home for survival.
Near-Earth asteroids in space continuously threaten life on Earth.
Earth has been hit by asteroids many times. Most burn up in the atmosphere, and the few that penetrate fall as meteorites. Only 3% of Earth's surface is inhabited, so the chance of humans being hit is minimal. But a large asteroid impact would have widespread effects. 65 million years ago, an asteroid about 10 kilometers in diameter hit Earth, causing the extinction of dinosaurs and the disappearance of at least 45% of species.
Unfortunately, observational data shows that a massive asteroid in the outer solar system is on a collision course with Earth.
It's projected to hit Earth within the next 100,000 years. So we need to develop technologies to sustain life on other planets. And there's another very real threat: climate change. Climate change is causing extreme weather globally, and global warming threatens human safety, agriculture, water sources, and more. For example, in early 2022, the extreme winter storm Eunice swept across Europe, causing multiple deaths and significant property damage. If humanity doesn't take measures to mitigate global warming, by 2000, the global average temperature is projected to rise by 3.2 degrees Celsius. Polar ice caps will melt, causing sea levels to rise by several meters, submerging most islands and coastal areas. Factors like mass displacement, population-resource imbalance, natural and man-made disasters, asteroid threats, and climate change constantly threaten human life on Earth. However, these problems aren't enough to force or encourage people to settle in space immediately. George Mallory explained that he risked climbing Mount Everest because it was there. Author Wanjek transposes Mallory's view to space exploration, believing that humans venture into space because of the desire to explore and the instinct to conquer the universe. But is space travel safe? Is current scientific and technological development mature enough?
Next, in part two, we'll reveal the challenges facing space travel.
Without Earth's protection, humans face threats like high energy particle radiation, insufficient gravity, lack of air, extreme pressure and temperature, even mental illness from prolonged confinement in cramped spaces. NASA's Human Research Program Roadmap has identified 34 confirmed health risks and 232 suspected risks from manned spaceflight. First, let's discuss the gravity problem. Sci-fi fans envy astronauts floating freely on space stations in TV footage, but reality isn't so picturesque. NASA research shows prolonged zero-gravity exposure harms health in multiple ways, as humans are fully adapted to Earth's gravity. Without gravity, calcium leaches from bones, muscles atrophy, blood vessels distort, causing eventual blindness. ISS astronauts must exercise 2 hours daily to slow bone loss, yet their bone density still drops 1% monthly, equivalent to an Earth senior's annual loss. Science Advances published twin astronaut research showing 25 months in space causes DNA mutations and brain shrinkage. Scientists try countermeasures like medication and compression leggings, but these only mitigate rather than prevent weightlessness effects.
The only viable solution currently is creating artificial gravity.
Artificial gravity works by rapidly rotating habitats so centrifugal force equals Earth's gravity, replicating conditions for bodily systems. No need to worry about dizziness. Surrounding references remain stationary, just like standing on Earth doesn't cause vertigo. Japan's Kibo module on the ISS has confirmed artificial gravity's feasibility and effectiveness. Russia plans to attach an inflatable rotating module to the Zvezda service module by 2025. Next, let's discuss two radiation threats: relatively controllable solar radiation and more dangerous cosmic rays. These radiations originate from plasmas composed of charged particles. Fortunately, Earth has robust armor. Its magnetosphere and atmosphere deflect radiation toward outer space or block it from harming life. No other celestial bodies discovered in space possess this protective armor. Once humans leave Earth for space, they must directly confront radiation threats. Solar radiation dangers are relatively manageable. Spacesuits and spacecraft hulls block routine solar radiation, while during solar storms, existing monitoring provides early warnings for astronauts to shelter during storms, but cosmic rays pose greater threats with no current warnings or reliable protection. Originating beyond our solar system, these cosmic rays bombard astronauts from all directions constantly. Current suits can't support long-term exposure. Long-term exposure to these ever-present rays gradually compromises astronaut safety and health. So how can we reduce cosmic ray impact? Recent research shows hydrogenated boron nitride nanotubes can effectively block cosmic rays under extreme heat or pressure, potentially becoming primary spacecraft material. CERN developed an artificial magnetic field 3,000 times stronger than Earth's, capable of protecting astronauts. We hope these emerging materials and magnetic fields can soon be deployed to ensure space travel safety. Now let's discuss temperature, pressure, and air challenges. Pleasant temperatures, optimal air pressure, and breathable air, free and abundant on Earth, become precious commodities in space. Earth's atmosphere acts like a thick quilt, allowing solar radiation to warm the planet while absorbing and redirecting Earth's outgoing heat.
This creates Earth's delicate dynamic balance between heat absorption and loss.
Thus, the atmosphere maintains Earth's temperature within an ideal range and enables cyclical variations. Celestial bodies without atmospheric protection, like the Moon, aren't so fortunate. Without an atmosphere to retain air, generate wind, and cycle heat, the Moon's day-night temperature difference can reach hundreds of degrees Celsius. Beyond maintaining suitable temperatures, the atmosphere provides pressure. Proper pressure prevents liquid water from freely expanding. On Mars, with just 1% of Earth's pressure, without pressurized suits, water in human blood would boil within seconds, instantly killing all liquid-dependent life. Current solution: practical, humans rely on spacesuits and spacecraft to maintain pressure and temperature in space. The atmosphere's most direct function is providing life-sustaining oxygen. Through photosynthesis, Earth's plants absorb our exhaled CO2 and release oxygen, a natural air regulation system enabling free breathing. In space, air regulation relies on chemical processes, absorbing CO2 and electrolyzing water to release oxygen, maintaining Earth-like air composition. Innovative, dual-purpose research spacecraft cultivation, improving hydroponics to simultaneously regulate air and provide food. Thus, safe space travel requires solving gravity, radiation, and habitat issues. With current knowledge, long-term space travel remains extremely challenging. But with continuous technological breakthroughs, space settlers may soon become reality. Now for part 3. Reaching space requires escaping Earth's gravity. First, achieving Earth orbit demands acceleration to 8 kilometers per second to maintain low Earth orbit, consuming massive fuel to overcome gravity and atmospheric drag. At that speed, on Earth, traveling from Shanghai to Beijing would take just 2.5 minutes. Once in low Earth orbit, as spacecraft move farther from Earth, gravitational influence weakens. The craft can then accelerate further with less energy. Approximately 12 kilometers per second reaches near-Earth asteroids, 14 kilometers per second the Moon, and 16 kilometers per second Mars. Well, to achieve sufficient speed, rockets typically require massive amounts of chemical fuel. About 90% of a rocket's mass is fuel. 8% is the metal casing containing it, while only 2% is actual payload, making launches extremely costly. End quote. Launching 1 kilogram into space costs approximately $15,000. Imagine the staggering cost if you brought luggage on a space trip. So how can we reduce space access costs? Tsiolkovsky's famous rocket equation forms the cornerstone of modern astronautics. This equation shows cost reduction requires either improved fuel efficiency or reduced mass.
Modern rockets already use lightweight materials and staging to jettison empty tanks. Little mass remains to cut.
Thus, we must focus on enhancing fuel efficiency in vehicle design. First, improving fuel efficiency. Current rockets use mixtures like liquid oxygen and kerosene or liquid hydrogen, with exhaust velocities maxing at 4.4 kilometers per second.
Scientists research new propellants, including Harvard physicist Isaac Silvera's team, who created metallic hydrogen, solid-state hydrogen.
Using metallic hydrogen propellant could increase exhaust velocity to 16 kilometers per second. This propellant drastically reduces fuel consumption and rocket mass, potentially slashing launch costs by hundreds of times. Stably producing and storing metallic hydrogen remains the critical engineering challenge. And beyond metallic hydrogen, proven technology, nuclear fuel offers immense power in compact form with fission technology matured through nuclear plants and submarines. Nuclear fission involves heavy atomic nuclei splitting into lighter nuclei. Per Einstein's mass energy equivalence, fission releases energy from mass defect. Releasing enormous energy nuclear propulsion could theoretically achieve spacecraft speeds of hundreds kilometers per second, reducing costs thousands-fold. In the 1950s, Project Orion, led by American physicist Freeman Dyson, employed nuclear-powered rocket systems, later halted due to insufficient funding and radiation fears from potential launch explosions. Capitist. The U.S. government canceled the project in the 1960s, so humanity never achieved nuclear-powered rocket launches. What about nearly radiation-free fusion? Hans Bethe, 1967 Nobel Physics laureate, proved colliding deuterium and tritium nuclei at high speed releases enormous energy. This unveiled the mystery of nuclear fusion.
The terrifying hydrogen bomb was developed from this principle.
Hydrogen fusion far surpasses fission in power with extremely short-lived radiation. Thus, using hydrogen fusion as rocket fuel would provide virtually limitless cheap fuel, reducing space transport costs to near negligible levels. However, fusion requires temperatures exceeding 100 million degrees Celsius. Currently, humans can only trigger fusion using fission heat, with no stable controlled fusion engine systems developed yet. Beyond fuel efficiency, transport innovations include SpaceX's reusable rockets, commercial spaceplanes, and sci-fi concepts like skyhooks and space elevators. Let's examine each. SpaceX, founded by Tesla's Elon Musk in 2002, developed partially reusable Falcon 1 and Falcon 9 rockets. Traditional rockets are disposable. After launch, fuel tanks and boosters, comprising approximately 70% of launch costs, are discarded. SpaceX redesigned key components enabling stable booster landings, followed by brief inspection and maintenance. Reusing components within weeks reduces launch costs by tenfold. Launch costs per kilogram dropped to around $1,400, winning SpaceX substantial commercial orders.
Commercial returns fund ongoing R&D. Musk stated SpaceX aims to reduce low-orbit launch costs to $10 per kilogram.
Beyond SpaceX, more companies achieve breakthroughs in manned spaceflight. Bigelow Aerospace plans future space hotel operations. Blue Origin, founded by Amazon's Jeff Bezos, focuses on space tourism, while Virgin Galactic offers low Earth orbit flights with bookings available. So how can we reach space hotels quickly and comfortably? That brings us to spaceplanes. Until now, rockets were the only space access method. However, their comfort and safety aren't suitable for mass tourism. Since the 1980s, Britain's Skylon spaceplane development features hybrid engines, air breathing at low altitude, switching to rocket mode in thin air. This clever design enables comfortable space access at lower costs, delivering business class-like space travel experiences. Blue Origin's suborbital flights and Virgin Galactic's Spaceship Two both use similar designs for human space tourism. Beyond rockets and spaceplanes, are there cheaper space access methods? No, Tsiolkovsky proposed space elevators in the late 19th century. Anchor a platform in geostationary orbit, 36,000 kilometers high, extend a tether to Earth, transporting people or cargo via elevator.
Sustainable energy solution. Solar panels would power the elevator's ascent to the platform.
Once built, space elevators could become our cheapest space access, potentially just dollars per kilogram, requiring minimal energy to reach distant space from the platform. Though appealing, space elevators remain nearly impossible with current technology. First, we need a 36,000-kilometer-long cable that can withstand such immense weight without breaking. Only carbon nanotubes can do that, but the longest produced is only half a meter. I'm broken, Marion, Dozens 1. Secondly, even if we can manufacture large quantities of connected carbon nanotubes, we must consider anchoring points to avoid aircraft collisions, space debris, and terrorist attacks. I think that's additionally, there are issues like pressure and gravity during the elevator's ascent. Despite technological progress, space elevators on Earth remain nearly impossible. But inspired by the concept, someone proposed the skyhook system, a platform in low Earth orbit connected to a cable with a hook or magnet. The hook or magnet hangs at the atmosphere's edge via cable. Cargo or crew capsules are attached using balloons or spaceplanes, then pulled to the orbital platform. In the 1990s, Boeing simulated the skyhook system, verifying its feasibility. More excitingly, mass-produced high molecular weight polyethylene cables meet skyhook weight and toughness requirements. However, despite proven technical feasibility, the skyhook wasn't implemented due to economic constraints. Developing such a system requires trillions in investment, unaffordable for any entity. But new fuel propellants and transport modes will keep reducing space travel costs. Finally, let's envision settling and living in space. On July 21, 1969, American astronaut Neil Armstrong aboard Apollo 11 became the first human on the moon, a giant leap for mankind. In 2009, India's Chandrayaan-1 probe found widespread water molecules on the moon, some areas up to 30% water, reigniting lunar exploration. People imagine lunar habitation possibilities, but even with water, life's source, living on the moon poses huge challenges. Moon gravity is 1/6 Earth's. Its thin atmosphere, about 100,000th of Earth's, is near vacuum. Day-night temperature swings reach hundreds of degrees Celsius.
Without atmospheric and atmospheric protection, cosmic radiation constantly threatens life.
Therefore, lunar bases must be built underground or covered with over 2 meters of lunar soil to protect humans from radiation. Another critical issue: one lunar day equals about a month on Earth. The prolonged night severely restricts plant growth. Though these issues make the moon unsuitable for long-term human habitation, they don't diminish exploration enthusiasm. Probe data shows the moon contains two rare Earth resources, helium-3 and rare earth minerals. Successful lunar mining would bring tremendous benefits to humanity.
Helium-3 is crucial for nuclear fusion. 200 kilograms could power a metropolis like Shanghai for a year.
Earth has less than 1 ton of proven helium-3 reserves, while the moon has over 1 million tons. Lunar mining could solve Earth's energy and environmental crises. Lunar rare earth minerals also attract significant attention.
Rare earth elements are vital in electronics, earning the nickname industrial vitamins.
A single iPhone uses 17 rare earth elements. Earth's mining grows harder and more polluting, making rare earths increasingly expensive. The moon has abundant rare earth deposits, and its low gravity allows relatively easy extraction and transport. So, with current technology, the moon won't support long-term human settlement for the foreseeable future. The author believes the moon will develop as a combined scientific exploration and industrial zone. We could establish research bases where scientists conduct in-depth studies using supplies transported from Earth. If robotic mining matures, humans could remotely operate robots for extraction and even on-site processing. Since the moon isn't suitable for long-term settlement, we turn to another popular space destination, Mars. If humans permanently settle on another celestial body this century, it will be Mars, the only solid body providing suitable gravity, temperature, and all essential chemical elements. Mars's gravity is twice the moon's, about 38% of Earth's, so its effects may be less extreme. Daytime temperatures reach 20 degrees Celsius, while nights drop to minus 100 degrees Celsius. Similar to Earth's poles, NASA and CSA's integrated system, rover, drill, oven, and lab, uses solar energy to extract oxygen and water from Martian rocks, solving breathing and drinking challenges. NASA's MOXIE instrument converts abundant Martian CO2 into oxygen and methane fuel. Mars' 24-hour, 37-minute day-night cycle, with approximately 12 daylight hours, supports plant growth, making farming significantly easier. Scientists have simulated crops in Martian soil. Onions, garlic, lettuce, sesame, sweet potatoes, and kale thrive abundantly. However, settling Mars still confronts atmospheric pressure and cosmic radiation threats. With thin air, 600 pascals average pressure less than 1% of Earth's, and no magnetosphere, humans need spacesuits and pressurized habitats. For cosmic radiation, artificial magnetic fields could deflect particles from Mars. Atmospheric pressure thus becomes the core challenge for Martian settlement. Scientists propose terraforming Mars, creating an artificial atmosphere. The specific steps are as follows. First, build factories releasing greenhouse gases like CF4 and C2F6. Absorbing sunlight would raise temperatures 4 degrees Celsius in 20 years, releasing polar CO2 ice into the air. This new atmosphere would provide suitable temperatures and adequate pressure. Next, adjust atmospheric composition, reducing CO2 and raising oxygen, enabling humans to live freely without suits. Once humans settle Mars, radiation, temperature, and light exposure will dramatically alter their appearance compared to Earth humans. First, the obvious changes might be to the eyes and eye sockets. Since Mars is farther from the sun and gets less sunlight than Earth, humans would evolve larger pupils to capture more light. And the skull would evolve too to fit those bigger eye sockets. Secondly, Martian human skin color would change. Increased radiation boosts melanin production, darkening skin. New diets could cause other pigments to build up in the skin. Meanwhile, plants Animals and microbes settling Mars with humans would evolve to adapt, possibly forming new species. Lessons from lunar and Martian exploration will help us boldly visit other planets. With ongoing aerospace breakthroughs, humans will head to more habitable star systems, travel the vast universe, and become space settlers. That wraps up our book interpretation. Reading notes are below the audio, and we'll see you next time.